work. So hey everyone, my name is Arthur and I'm part of the design research group here at Autodesk. If you've heard of Autodesk in the last 35 years of its existence, then you probably have heard of the name of our most popular product, AutoCAD, which helps architects lay out and design buildings. And if you know somebody who studied architecture, then you probably know that they're very familiar with our products, since it's kind of the standard tool for the building and construction field. But since the company's early days of AutoCAD, the portfolio of products has expanded to over 100 software products, touching different industries from design, such as product design, automotive, manufacturing, and even media and entertainment. And fun fact, like 90% of the Hollywood movies you see are actually using our media and entertainment products for modeling, lighting, rigging, or special effects. But what we probably don't know is that Autodesk has also dabbled in the medical field, specifically with design of medical implants, with the acquisition of this Within technology product 5 years ago. Within is essentially a latticing technology that takes into the account the forces and loads the part experiences for lightweighting as well as osseointegration. Since the forms that are produced are really complex, the only way to really produce these parts is to 3D print them. What you see here in this slide is Within applying its latticing capabilities to a cranial flap that conforms to the curvature of the skull. Medical engineers are essentially using this technology to design porosity of these implants with the lattices. And the project here involves 22 partners from 7 different European countries working to achieve an integrated supply chain for the design and manufacturing of a fully patient-customized cranial, dental, and spinal implant. The Within technology has already been used with over 45,000 patients since 2014. But the technology that I'm here to talk about today is one that we've been developing in research for the last 3 years, and we're calling it Generative Design. Essentially, it's a system powered by machine learning and cloud computing to create hundreds, if not thousands, of solutions to a goal-driven design problem. We see this tool being helpful for designers who want to explore form, like this chair you see on the left, or engineers looking to lightweight a design space, such as this cabin partition on the right for Airbus's commercial planes. In the case of the partition, the goal given to the generative system here was to reduce the weight while maintaining structural performance. The system then runs through hundreds of options, evaluating for its performance and weight criteria. The final design is a 3D printed aluminum and assembled partition that weighs 66 pounds, which is 45% lighter than the conventional partition, which results in huge savings for both fuel and carbon footprint. In the case of the chair, we were generating for wood and not for 3D printing, but for CNC routing construction, which is a more typical fabrication technique for mass production. But here we wanted to have the generative system give us all the framing options for having someone sit 18 inches off the ground and weigh a max of 300 pounds. So the software runs through all these possible solutions, and the designer guides the system on which versions are most promising and which ones need to be reiterated on and refined. And so the final solution that we chose is 18% lighter and decreases the displacement of the chair by 90%, as well as decreases the max stress by 78%. So the case study I wanted to talk about today is something I worked on with an intern, kind of a side project to help a friend of a friend design his own cast. So this is Seth, who I met through a mutual friend, and he was looking for an alternative to his cast after he injured himself in a bike accident. And the cast he came back with from the hospital was, uncomfortable, itchy, unattractive, non-waterproof plaster cast. And anybody who's broken a bone and needed one of these understands the desire for an alternative solution. So he heard of our facility and our technology, and he got into contact. And I jumped on the opportunity since I know it made sense to apply generative design to this problem space. Because not only was the need of lightweighting and customization to the topology of his arm already a given for the system, but the fact that generative design can maintain structural integrity while around the injured bone meant that we could serve the need of recovery while providing solutions that are adjacent to the problem of comfort, water resistance, or style by the way of 3D printing. So two big desires from Seth when we started the project was that he wanted to clean his arm, which he felt aided in the health of the process. And the other was that he wanted to see his injury to understand the stage of recovery, which he also felt from a mental standpoint helped in the healing process. He described the traditional cast as like a smelly black box. So we got started, and the first step was to scan his arm. Here I'm using an Artec laser scanner. And since this is very much a prototype test project, we started with laser scanning his good arm first, which we would plan to mirror the final solution to fit his injured arm. And so once we had the scanned arm, we then modeled a surface that fit around the unique curvature of his forearm, wrist, and hand. And the laser scanner pretty much has sub-millimeter accuracy, so we have confidence that we could get a comfortable and customized fit. Next, we applied the forces in generative design where we knew we wanted to keep the material, and specifically to the joint between the thumb and the wrist where the injury was, as well as where the cast would be experiencing forces throughout its daily use. The solution that the generative design system came back with is what you see on the right. The model was then split into two parts to assemble onto Seth's arm, and then modified to have interlocking mechanisms to attach both parts together. Once the model had its necessary parts, we began printing. We used the Fortis Stratasys printers, which print engineer-grade performance plastics like ABS and ASA. And then once we had the parts coming out of the printer, we met with Seth regularly to test the fit and the comfort of the cast, making small tweaks that ran for maybe 5 iterations before we finalized on the final one. And a big reason why we had so many iterations was that when we removed his original cast and tried to put the mirrored version onto his actual injured arm, it didn't fit, and we kind of learned the hard way that our bodies aren't completely symmetrical. So I mean, if we started with the scan of the injured arm from the beginning, we could have cut down that time. The total time for scanning, generating, tweaking, and modeling probably would have been 32 hours, and we took about 2 weeks to do the tweaking. But I think if we can get the software to have an automated workflow in place, we could bring that down to a day's work. And the bottleneck really for our process was the printing time, which took about 18 hours to print a full cast. But given that you can leave a printer on overnight, we really don't see that as too much of a hurdle. The real hurdle actually was having Seth's doctor approve of the process. I mean, in the end, the doctor didn't want to be a part of the design process, and so Seth and I took to designing the cast ourselves, considering what we knew about his injury. And the project, was more of a proof case to show that you can improve something like cast with these new emerging technologies, and not only make one that fits the same recovery needs as a traditional cast, but also make one that fits the user's daily life. Yeah, so that's me.
Arthur, that is so awesome. I know we talked quite a bit. You shared the process with me, but to see the photos and to hear it's pretty amazing. As you can see, people are chatting about, many people here said, pretty much everybody agreed that they would prefer a 3D printed cast any day over the traditional cast. So I think there's definitely something there.